This video is for topic 4.7, types of reactions. The objective for this topic is to identify a reaction as acid-base, oxidation-reduction, or precipitation. Let's start with precipitation because this is something that we've already talked about in previous topics. So we've already talked about net ionic equations. So net ionic equations are used whenever we have a precipitation reaction or potentially to show that there is not a precipitation reaction. To show that everything is aqueous. So as a refresher, net ionic equations are the final result of basically 3 steps. So we have a molecular reaction equation, which shows complete formulas. So how we would normally write a chemical formula for a compound, whether it is solid or liquid, gas, or aqueous. Then we have a complete ionic reaction equation, which shows all the components of a reaction, but broken apart into their separate ions. So anything that is marked or labeled as aqueous means that it dissolves in water. So that means it's going to separate into its 2 ions. You'll want to keep in mind that when we are dealing with polyatomic ions, they're not separating into their separate elements. They separate into their ions. And then anything that's a solid or a liquid or a gas stays in that solid, liquid, or gas form. So in our example reactions, we had silver nitrate with potassium chloride reacting to form silver chloride and potassium nitrate. So silver nitrate in the complete ionic equation separates into silver ion and nitrate ion. The potassium chloride separates into potassium ion and chloride ion. The silver chloride, since it's labeled as a solid, since it is insoluble in water, stays together as silver chloride. And then potassium nitrate, since it is aqueous, splits apart into its potassium and nitrate ions. And then finally, we have our net ionic equation, which leaves out our spectator ions. So spectator ions are the ions that show up in both your reactants and your products of your reaction equation in the exact same form. Basically means they don't do anything in the reaction. So in our example, nitrate shows up before and after as an ion, and potassium shows up before and after as an ion. This leaves us with silver ion and chloride ion to form silver chloride. In order to write net ionic equations, you will want to be familiar with your solubility rules, which are general rules for what will and will not dissolve in water, as well as some of the more common exceptions to our solubility rules. Next, we have acid-base reactions. Acid-base reactions involve transferring one or more protons between chemical species. To help you better identify an acid-base reaction, you will want to know your strong acids, and there are 7 of them, and they're listed below. However you need to memorize this is what you need to do. So whether it's flashcards or Quizlet or working with each other or just staring at the list, whatever it is that's going to help you know your strong acids is going to help you better identify acid-base reactions. And then finally, we have our redox reactions, where acid-base involve transferring one or more protons or hydrogens. Redox reactions involve transferring one or more electrons between chemical species. These also include combustion reactions. There are 2 different ways to identify whether something is going through oxidation or reduction, and both involve memory devices. So you can remember it as oil rig, where oxidation is loss of electrons and reduction is gain of electrons. So OIL, oxidation is loss, RIG, reduction is gain. So oil rig. Or you can remember it as Leo the lion goes grr. Leo being loss of electrons is oxidation, and then grr being gain of electrons is reduction. So loss of electrons is oxidation, gain of electrons is reduction. Whichever way helps you remember it, great. If you have a different way, that works fine too. Personally, I prefer oil rig. It's just the one I've always used. My best friend uses Leo the lion goes grr. Whatever makes you happy and helps you better remember which one is oxidation and reduction works great. In order to identify this, we have to be able to write oxidation numbers for our different elements. And there are some rules to follow when writing oxidation numbers. First, each atom in a pure element has an oxidation number of 0. For monatomic ions, the oxidation number is equal to the charge of an ion. So if you have silver +1, the oxidation number is +1. When combined with another element, fluorine is always going to have an oxidation number of -1. So if it's overall neutral, and you know that you have one fluorine, you know that the other element is going to have a +1 oxidation number. These are very, very, very similar to charge. The oxidation number for oxygen is -2 in almost all compounds. Chlorine, bromine, and iodine have an oxidation number of -1 in compounds, except when combined with fluorine. Then they're going to have a +1 because fluorine is always going to have a -1. The oxidation number of hydrogen is +1 in most compounds. And then finally, the algebraic sum of the oxidation numbers, so basically when you add them all up, a neutral compound has to be 0. If it's a polyatomic ion, it has to equal the ion charge. So you're probably looking at this list and going, how is this different than figuring out the charges? It's really not. When we're talking about redox, though, we use oxidation numbers because remember, we're transferring electrons. So the charges aren't always the same. So it's usually pretty easy to start with things like oxygen because oxygen is going to be -2 in pretty much everything. And then start with hydrogen because hydrogen is going to be +1 in almost everything. And then from there, you can figure out what numbers have changed. Keeping in mind that in the end, if you have a neutral compound, all the oxidation numbers have to equal 0. If it's a polyatomic ion, so it has a charge, then all the oxidation numbers added together need to equal the charge of the ion. So we can use our oxidation numbers to then look and determine, did an element gain or lose electrons by its change in oxidation number? If your oxidation number gets more positive, it's losing electrons. If your oxidation number gets more negative, it's gaining electrons. So that's how we can use our oxidation numbers to decide if something is going through oxidation or reduction.